Hello everyone. In this video, we're going to be talking about how to predict the sign of delta H and delta S. So remember, the delta H is the heat of the reaction, also called enthalpy, and the delta S is going to be your entropy of the reaction. And we will talk about how you're going to be predicting their signs, but eventually I'll talk about how to use the bond energies to figure out the delta H of a reaction. So before we jump into there, let's talk about a few terms there. The exothermic reaction are going to be the one that releases energy. So if I have a reaction where A plus B is going on to make C plus D, one way of writing this particular reaction, if it is indeed an exothermic reaction and releasing energy, the delta H would have some sort of negative value. All right, so negative, some sort of kilojoules per mole there. That's one way of writing it. The second way of writing this particular reaction, and that's sometimes also seen, if you can have the energy added on the product side. So energy added on the product side and writing that in the form of delta H to be negative is actually the same thing. So that's what makes an exothermic reaction. Then you can also have an endothermic reaction where you actually going to be requiring energy for those to take place. And let me take a simple example where I got C plus D going back to the A plus B. So now what I just really did is just wrote the top reaction, but just in the reverse direction. So remember, if your one-way reaction is exothermic, going other way is going to be the endothermic. So if this reaction is endothermic, I'm going to be having a positive value for the delta H per kilojoules per mole. And that's one way of writing it. The second way of writing this particular equation would be I can have your energy added onto the reactant side. So plus energy right here. So you want to make sure you're familiar with how you're going to be writing these exothermic and endothermic reactions um, two different ways. And then when it comes to predicting the delta H of a reaction, if you're making stronger bonds and if you're breaking weaker bonds, then your overall delta H is going to be negative. So let's say, so anytime I can say the stronger bonds are made and your weaker bonds are broken, then your overall delta H of the reaction is going to be negative, which means it's going to be exothermic, and the opposite is going to be true in terms of endothermic. If you're making weaker bonds, but then you're breaking stronger bonds, then your delta H is going to be endothermic. And then the question is, how do you really know if you're breaking a stronger bond and a weaker bond? And sometimes you just have to use your logic, and sometimes you may be given those bond dissociation energies that I'll talk about them in a minute. The second thing I do want to mention here is the entropy. Entropy is actually going to be the measure of disorder and randomness, or how chaotic something is. And if you increase the entropy going from a reactant to product, then your delta S is going to be having some positive value. And if you decrease the entropy going from reactant to product, then your delta S is going to be a negative value. And I'll talk about, well, there's the typical units for those is going to be joules over Kelvin. That's another thing you want to keep in mind. It is a temperature dependent. So if you increase the temperature, obviously things going to move faster. They are going to be more chaotic. Um, Let me take a few examples to kind of clarify things. Suppose I have H2O solid, which means I got the ice, and this ice is being converted into the liquid water, so H2O liquid. So who is going to be more chaotic, the solid or the liquid? Well, typically your liquid can move around easier than your solid. If you spill the water, it's going to go everywhere, but if you spill just a piece of ice, it's just going to stay out one place. So liquid having a higher entropy, your delta S for this overall reaction is going to be a positive. Now, we're not really asking you to calculate what exactly going to be. We're asking you to be able to predict what your delta S going to be. Well, what about what's delta H going to be here? Well, we're not really breaking any bond here. So this is another thing you want to make sure you are able to look at it and able to identify the sign of the delta H. When you're going from solid to a liquid, or another way of saying, if you have an ice sitting on the table, under what condition it's going to melt? Well, the answer is if the temperature is big enough, or if it's less than zero, it's not going to melt. It's going to melt only if it reaches zero, if it goes, or if it goes over zero. So that means it's actually going to be requiring energy when you're going from solid to a liquid. So delta H for that particular case is going to be an endothermic process. So it's going to be a positive sign there. Okay, I can take maybe another example where I can talk about CO2 gas, carbon dioxide gas, is changing to CO2 solid. So this is called in a dry ice. So now you're going from a gas to a solid. So what's really going to be happening to the entropy here? Well, remember your gas is going to have the most entropy out of all the different phases because they can move around very easily compared to the solids and even compared to the liquids. When we're looking at going from the reactants to the products, you are going to be decreasing the entropy. So your delta S is going to be negative. What about the delta H? Well, you can actually predict the delta H here because it's going to be a exothermic reaction because you're going to be making these interactions here. You're not really making the bonds here, but think about this, that when the carbon dioxide is a gas, you have individual carbon dioxide molecules on their own. But when it's made the solid, now you have some sort of intermolecular interactions going on between the carbon dioxide molecules. And they very well could be the dispersion forces because overall carbon dioxide is a nonpolar molecule. Whenever you're making interactions, it's still going to be releasing energy, and since it's going to be releasing energy, your delta H is going to be negative for that particular case. So just not only you are going to be looking at what's going to be the delta H when you breaking or making the bonds, but you can sometimes you can also rely on when you breaking or making the interactions, and that's usually happens in case of phase changes. But obviously, most of your chemical reactions don't even involve phase changes, but they are just going to be the bond breaking and bond making. So how do you take that into account? To find the delta H for those particular cases, let's suppose I got the delta H of a reaction is going to be equal to the sum of all the delta H's where you are breaking the bonds plus the sum of all the delta H's where you are going to be forming the bonds. So obviously this is going to be looked at the reactants, like how many bonds you're going to be breaking, and this is going to be being looked at the product, where you're going to be looking at how many new bonds you're making. And the other thing you want to make sure, like where these delta H values going to be coming from for the breaking bond, those are going to be your bond energies or the bond dissociation energies. So what's really the difference is between the bond dissociation energy and the bond energy. Well, the bond energy is just going to be the average of bond dissociation energies. And I'll give you a simple example here. So suppose I got a CH4. Now I have four CH bonds there. Okay, so I got four CH bonds there, and all four of those could have a very well different bond dissociation energy. Another way of saying, if I break the first one, when you're breaking the second one, it may not have the same bond dissociation energy. So they could very well have four different bond dissociation energies. But when we're talking about the bond energy, we're going to be looking at what's going to be the average of those four bond dissociation energies, and that's what we're going to be using for the most part in the calculations. So I can talk about, I got four CH there, and if I want to calculate the bond energy here, I would do the CH of one bond plus the CH of the second bond plus the CH of the third bond, and then the bond dissociation energy of the fourth bond, and divide all those by 4 to get the average, and that's going to be your, obviously, whatever the CH bond going to be, that's going to be called your bond energy. So you are it's important to know the difference between the bond dissociation energy and the bond energy, but for the most part, you guys are going to be given the bond energies in a given example. The other important thing you want to make sure you know your the bond energy is like here. Let's go back and erase this, maybe change the color. The bond energy of these reactants, since you are going to be breaking the bonds, so breaking bonds is always going to be a endothermic reaction. So those are going to be positive. So whatever value you are going to be given, you're going to be taking those as positive because remember that's going to be your endothermic reaction because they require energy. But when you're making bonds is always going to be exothermic. You're always going to be releasing that much energy whenever you're making a particular bond. So these bond energies, when you're forming the bonds, are going to be taking as negative. So that's why it's going to be exothermic. So remember what we said earlier. If you are making stronger bonds, and you're breaking weaker bonds, then your overall delta H is going to be a negative value, because, and then in that case, overall delta H would be exothermic, and that's because we can come down here. If you are breaking more, if you are making stable bonds, or if you're making bonds that are stronger, you're going to have a bigger value for this side right there. And since you have a bigger negative value, your delta H of the reaction overall is going to come out to be a negative. So that's why it's going to be a exothermic reaction in that particular case. So let me take an example here just to kind of clarify things. Suppose I got this reaction here and I'm given these bond energies on this left side. I don't really have to worry about what's going on with everything, but the most important thing is what bonds are broken and what bonds are going to be made. Okay, so let's look at what bonds are going to be made and what bonds are going to be broken. So bonds broken, when I'm looking at my reactant, we got four carbon hydrogen bonds, and obviously we're going to have a chlorine chlorine bond. And when we're looking at the products, we still have three carbon hydrogen bonds, but then one new bond that's formed is carbon chlorine, and another new bond that's formed is a hydrogen chlorine. So you must be breaking one of the carbon hydrogen bonds. You're not breaking all four of them, and you don't really have to worry about the other ones. Just focus on the one that are being broken and the one that are being made. And the one that stays same on the both sides, don't even worry about those. So the other three carbon hydrogen bonds that are staying the same on both sides, we're not going to be worrying about them. So bond broken is going to be carbon hydrogen and chlorine chlorine. And then what about bonds made? The bonds that are going to be made would be carbon chlorine and then hydrogen chlorine. So at the end of the day, when I'm trying to figure out what's going to be the delta H of the reaction here, I'm looking at the bond broken. So that's going to be the delta H of your carbon hydrogen bond plus the delta H of your chlorine chlorine bond. So those are going to be your bond broken plus the delta H of your carbon chlorine bond plus your delta H of hydrogen chlorine bond. So those are going to be your bond formed in this particular case. So now it's all about plugging in numbers. So delta H of carbon hydrogen. So remember, when you're breaking the bonds, you're going to be taking those as positive. So delta H for CH, or the bond energy, is 414. So I'll go ahead and write down 414 here, plus the CCl is going to be 243. So those are going to be your reactants, and then plus. Now remember, your product, since you're making the bonds, these sides are going to be your exothermic. They are going to be the one that's releasing the energy, because that's how it always works. Bonds made releases energy. So carbon chlorine bond is going to be 349. So I will go ahead and write down negative 339 rather. And then you're going to have plus, and then you got to have another minus for the HCl bond, which is going to be minus 431. Okay, so from here we just have to do our math now. So that comes out to be negative 113 kilojoules per mole. So overall, delta H of this reaction comes out to be negative, and since it comes out to be negative, it's still indeed going to be a exothermic reaction. So another way of saying you are making stronger bonds here. So I can say making stronger bonds, and you are going to be breaking weaker bonds. If the delta H was positive, then you would be making a weaker bond and you would be breaking the stronger bond in that particular case. So this is how you're going to be predicting the delta S and delta H, and even calculating the delta H using the bond energies. If you have any questions, feel free to leave any comments in the section below.